usually the best time. No one wants to go in a really cold swimming pool. It's 1,500 bacteria per cubic centimeter, and that's on Monday morning. Now, a cubic centimeter is roughly, I don't know if you can see, but this is like a little die here. It's not a square one, but that's about a cubic centimeter, okay? See how small that is? There's 1,500 bacteria in that amount of space in your swimming pool. Okay, and that happens at 8 a.m. on Monday morning. The count doubles every day, every 24 hours after that. Okay, so if you start, so we're going to fill out the table with what we think the bacteria count is. So at time 0, that's Monday morning, we said there were 1,500 bacteria. And if you're doubling, what are you multiplying by every time? 2. So on this is Tuesday morning, one day later, how much bacteria would be there? I know you all shouted that very loudly. You had 3,000 bacteria. What would be on Wednesday morning? 6,000, then 12,000. Yes, you don't have to say it. It's okay. I know you're quiet. 24,000, then 48,000. So that's Monday, Tuesday, Wednesday, Thursday, Friday. By Saturday morning, there are 48,000 bacteria in this little teeny tiny space of water. Yes, that is kind of disgusting, right? There's apparently no chlorine in this pool. So, okay, suppose we want to figure out the expected bacteria count at 2 p.m. on Thursday. That's 3.25 days after we started counting. So not a full 4 days. Let's make an estimation. What do you think the bacteria count might be? Just give me a rough idea here. So we're on Tuesday afternoon. So that's in between what two numbers? Between days 3 and 4, right? So pick a number in between there. How many bacteria do you think might be? 15,000? Okay. So maybe 15,000 bacteria. We're going to guess that because it's, I don't know, roughly between 3 and 4 days. We're at 3.25. Okay, so we're going to find out exactly. In order to do that, we need to make an exponential model. We're really good at knowing exponentials. We just had a quiz about them yesterday. So remember, your exponential model is in the form y equals a times b to the x, where a is starting off, b is the growth rate. How many bacteria do you start with here? 1,500. Okay. Now, in parentheses, what's the growth rate? What's happening to the bacteria every day? It's doubling. What number is doubling? 2. And then they want to use t instead of x. I mean, if you used x, I wouldn't yell at it. There's your model. So how do I use that model to figure out the time after 3.2, or the number of bacteria after 3.25 days? Put it in for t. So this is where your calculator is going to come in handy. The number of bacteria, population, I don't know how to write, after 3.25 days, we'll type into our calculator 1,500 times 2 to the 3.25 power. And let's see if we all get the same numbers. How many bacteria are there? We were close. 14,270-ish. Yeah, we were close, right? We were good estimators. So let's see, there would be 14,270. And in this unit, since it's, or in this problem, since it's an application, we have to include units. 14,270 means nothing in this problem unless you put the word bacteria on the end of it. I did linear modeling with my Algebra 1 today, and they did not like the fact that I made them put units on things, but that's the way the world goes. Okay, easy, right? Okay. Now, suppose we can use our graphing. I don't know who that is, but it's gone off a couple times now. Use your graphing calculator to graph the function. So we're going to adjust our window because if we have a y-intercept of 1,500, is that going to fit on our 10 by 10 grid in our calculator? No. All right, so let's go to y equals. Let's type it in. We're going to do a lot of adjusting of our calculators as we go through the rest of the year. So we're going to start by plugging our equation in. You have to use x, can't use t. Now, where's the y-intercept of that function? 1,500. So we need to make this scale. And here, this box is just what we're going to make our scale. So are we going to worry about negative x values for this application problem? Do I have negative days? No. So why don't we start our x minimum at 0? And how far out do you want to go? We can always adjust later, but how many days out? 10, 20, 50? What do you think? 10? 10 works. Let's start with 10, and then we'll adjust if we need. Yes, Charlie?
You can just go to Zoom to fit.
Yes, but Zoom Fit isn't great. I'm going to suggest you don't use Zoom Fit. And we'll go by 1 for X scale. And I'll tell you why later, but it actually doesn't make that good of a picture. We can make a better one by adjusting it. Y minimum, can I have negative bacteria? No, so let's start at 0. My maximum, my y-intercept's at 1,500, so I need bigger than that. What number do you want to make your y maximum? Any ideas? 60,000? Okay, let's do that. 60,000. And what do you think your scale should be? What's appropriate if I'm going from 0 to 60,000? Maybe like, I don't know, 10,000? We can go by 10,000. Your calculator can do that. So let's type that into my calculator. So how do I adjust the window? Do you remember? Go to window. Yes, Steven?
How do I do this on the Inspire?
I'll show you later. Not right this minute. The X's don't change. You can just watch for now. It's actually easy. It's under one of the, if you go to graph and type your equation and you go to one of the menu settings, you can change the scale. So we went 0 to 60,000, and we went by 10,000. So when I hit graph, you see a nice picture, right? Okay. So what was the point of this? Well, first of all, let's sketch our graph. So we are going to, we know that it kind of looks something like this, right? Just a sketch, doesn't have to be perfect. Now, we're going to use this graph. I'm going to show you a couple things here. So first of all, if you have a TI-84, which is like what I have on my screen, not a TI Inspire, I want you to follow these keystrokes. I want you to go to second, so hit the second button. Go to calc, which is your second trace. And we're actually going to choose number 1, which is value. I don't think we've done value yet this year. If I go to option 1, see on the bottom how there's an X equals with the cursor? You can type in your number. So say we want to find the value at 3.25, like we just did using our function. And you hit enter. See the flashing cursor now? Is that y value the same as the other y value we had? Yeah, so that's another way to evaluate your function. If you have a graph, you can trace it at a specific value. So you get the same thing here. So 14,000. Oh, that's your faces. You don't want to see those. 14,200. Here, grab a packet off my desk. Okay, now if nothing's done, so they don't put any chlorine in, and the bacteria continue to double and double and double, we want to know how long it will take for the bacteria count to get to 3 million bacteria in this teeny tiny little space. Would you go in that pool? No. That would be disgusting. Yes, I agree. So let's write an equation to represent the situation. So here would be my equation. 3 million, would that be the x or the y for my function? The y. So we'd write 3 million equals, and then just your regular equation, 1,500 times 2 to the x. Now, we actually don't have the tools yet to solve that by hand. We will learn that next week. But for now, we can't do that by hand, but we can solve this using our calculator or get a rough estimate. So first, I can look on my table. So everyone go to your table on your calculator. And we're going to scroll through there until we can estimate between what 2 days does the y value look like it gets to 3 million. Now eventually at 10, you see this 1.5 E6. Does anyone know what the E6 stands for? I'll write it down here. Yeah, so if I have 1.4 E6, that's the same as 1.5 times 10 to the 6. That's scientific notation. That means you move that decimal from the 5 over 6. So 1, 2, 3, 4, 5, 6. And fill in with zeros. That would be 1.5 million. Right? So we want 3 something with an E6 on the end. And it's 11. So it looks like it's between days 10 and 11 we get to 3 million. All right. So let's see. So between day 10 and day 11, we're going to, bless you, get to 3 million bacteria in that little teeny tiny spot of the swimming pool. Now, let's use the graph to exactly find it. Now, what was our y maximum on our graph? What was our window max? 60,000, right? Is that going to help me with 3 million? No, so let's change that y maximum. Let's make it 5 million. Okay. So 5 with 6 zeros. I think I had enough there. And let's make our scale I don't know, 50,000. So we'll still see the same kind of picture, but it'll help. I don't think my x's go out far enough, so maybe let's make our x's, well, we said it was between 10 and 11, right? So we really only need maybe 20. And we'll go by ones. Here we go. There, we can see a little bit better now, right? See how I troubleshooted that? Like, oh, I couldn't see, but we know it's going to be between 10 and 11, so I don't have to go farther out than 20. All right, now, how can I use the graph to help me solve this problem exactly? I need to graph something else. What do I need to graph in here? Y equals 3 million. That's right. So go up to your graph, go to the second line, type in y equals 3 million. Because when I hit graph, I'm going to get two graphs. And what feature of this system is going to tell me how many bacteria or how many days? Where they intersect. How do I intersect the graph or find the intersection? Second trace, and I go down to number 5, which is intersect. And I don't have to move the cursor, I just hit enter 1, 2, 3 times. And how many days exactly will it be? 10.966 days. So that is in between 10 and 11. Good? Makes sense? We're going to start using the calculator in a lot of different ways here. Okay? Second page. Alright, this is like my favorite example ever. You guys know the Sound of Music? Yes? Okay, if you didn't, if you don't, go home, tell your parents you need to watch the Sound of Music. It's a Sound of Music themed problem. It's great. Maria, who's Maria in the Sound of Music? The mom, right? So the nanny who becomes the mom. She was a former nun. She made a half gallon, 64 ounces of orange juice. Because she has a really big family, so they need a lot of orange juice. She made that on Saturday evening for Sunday morning's breakfast. In the middle of the night, Liesel, she's the oldest one. She's the one that like dances around the gazebo, wishing that she was 17 and she's only 16. She got really thirsty. She drank half of a pitcher of orange juice. All right, but she didn't want anyone to know, so she refilled that pitcher up with water. And so it was like half water, half orange juice. Not long later, Friedrich, the next one, the oldest guy who wanted to be a man. Do you guys remember this like at all? Am I just like talking? Kind of. It's fuzzy. Friedrich woke up. He did the same thing. He drank half the pitcher, but he didn't want anyone to know, so he refilled up again with water. Oddly enough, all the kids did the same thing. So let's figure out how much orange juice is in the pitcher after each refill. So how much did we start with? How much did Maria make? 64 ounces. Now after Liesel refilled the pitcher, how much orange juice was still there if she drank half of it? 32. How about after Friedrich? 16 ounces, right? It's mixed with water, but there's still 16 ounces of orange juice in there. Louisa, how much orange juice? 8. And then after Kurt? 4. Then Brigitte, it's only 2. Can you imagine like a half gallon of pitcher with 2 ounces of orange juice in it and the rest water? That'd be really gross. Yes, okay. Marta has 1 ounce and Gretel has half an ounce.
It was filmed in Austria.
Yes, it was. Have you ever, like, is that a big thing in Austria?
They showed it to us because they told us that all the Americans,
All the children
know
should
it,
know.
but we don't really know it.
No,
So.
that's a great. So my grandma, who she's passed away, but she had really bad dementia when like the last 2 years of her life. So we go to the nursing home, but like she couldn't really talk to us much, and when she did, she was very confused a lot. But she really responded to music. So like we would sing Christmas carols and stuff, and she loved the Sound of Music. So we'd be in the dining room, and she'd be kind of cranky and not eating. So we'd start singing like the Go a Dear song and stuff to her, and she'd start singing along. Like she remembered all the words to these songs, but she couldn't like tell me what my name was or what day, like anything like that. But so she loves Sound of Music. So we used to sing this to her a lot. That's my story. That's why I love Sound of Music, because it reminds me of grandma. All right, write a function for this equation. All right, so we always ask ourselves, what's the initial value? That's my A. And my growth rate, the B. So what would my equation be here? Y equals, how much do you start with? 64. And in parentheses? 0.5. Or 1/2 is fine to the x. Now this is decay, right? Because the B, the growth rate, is less than 1, and my table is going down. So let's use this equation. We can probably follow the pattern, but Sunday morning, George wakes up, George, I don't know, how would you say it, Kayla?
George,
George, okay. George wakes up early, morning, and he's so thirsty, he wants some orange juice before breakfast. He does the same thing all his kids does. They must have learned it from him. Using the function as well as the table, let's predict. So if we were using the function, what would go in for x? What person in line is he? He's the 8th. So if I use my function, I put 8 in for x. Let's just verify that we wrote the right equation. What do we expect his answer to be? How much juice? 0.14 or 0.25, right? So if I type that into the table here, I'll have, let's see, 64 times 0.5 to the 8th, and I do get 0.25. Quarter of an ounce of orange juice. It does seem disgusting. Now suppose this pattern continues for 20 people. They have a bunch of guests over. Will there be still some orange juice in the pitcher? Yes. How much? Let's see. Not a lot. You're right. 64 times 0.5 to the 20th. Oh, e to the negative 5. So let's see. 6.1 times 10 to the negative 5th. So that means I have to move that decimal 1, 2, 3, 4, 5 and fill those all in with 0. So there's 0.0000. I lost a 0. 61 ounces. Do you think you're going to taste the orange juice?
No.
Probably not, but there's still a trace amount in there, right? Could this pattern go on infinitely? Will there still be orange juice? Yes, there will still be. Will you taste it at all? No. Okay, so that's kind of a fun, gross example. They're both kind of gross, aren't they?
Yeah.
Sorry I started you off that way. All right, remember exponential modeling here? All right, let's move on to part 2. So this is basic exponential modeling. You're growing by doubling, tripling whole numbers, or like having something. Part 2 here is, let's see, pause.